So these are the last two problems on this handout, and there will be one like this on the exam, either this one or that one involving the arctangent and one involving the arcsine. There won't be anything involving the arcsecant as far as these more complicated problems. So the basic idea here is that we should be able to use completing the square to rewrite either the denominator, the whole denominator, or the denominator that's in the square root as a complete square. And then we have to, you don't have one of those? Yeah, just borrow a piece of paper and you can write it on a regular sheet because I don't know where they are. My office is getting piled full of things to do, so I'd have to dig through it and figure out where the heck it is. I'm lucky I didn't lose your tests. Okay, so and then what you'll do is you'll break the numerator up into two parts. One where the numerator is the derivative of the denominator in either case, and when you have this, you'll end up with an integral that involves the natural log plus the one that involves the arctangent. And in this case, you'll end up one that involves the square root of x, or square root of this thing, and also the arc sine. So let's go ahead and do these. You guys know how to do the completing the square, so why don't we have you do that first. So rewrite this one. Actually, why don't we do both of them? So rewrite that as a complete square. This one, you're going to factor out a negative sign. So I'll let you do that too. At least some of you knew how to do it, I guess. Not everybody. And you can have an odd number, an odd coefficient. Instead of 6x, I could have 5x. The only it just makes the problem more complicated. It's not like you can't do it. I guess theoretically you could have a decimal if you wanted to. It's just more laborious, but it's still doable. But we typically use even numbers just so that completing the square is easier for you guys to do. So one thing I was going to ask you guys has nothing to do with calculus was, does anybody have any interesting Christmas traditions that they're going to be celebrating this year? So give that a thought. I'm going to share, not that weird, it's just my English family traditions. So go ahead and do both of these if you haven't done both of them. You need to be working on it. Forgot my personalized microphone today, and so I'm using the old one. So go ahead and do the completing the square. Okay, so you've done that for that one. Yeah, some people, I don't know why. Oh, it's the last day of class, I'm not coming, or even the teachers do that sometimes. I never do that. We keep going. Got too much important stuff to take care of here. Uh-oh, sorry.
It's 23, not 25.
Oh, is it 25-3? Okay, sorry. Thank you. Okay, so the first one here, I add 9 and subtract 9, and that allows me to make this into a complete square. I don't have a nice complete square here. I have 14, so a is going to be the square root of 14. Over here, I've factored out the negative sign, so I take negative 4, divide by 2, square it, you get plus 4, but I'm really subtracting 4, so to balance that out, I add 4, which gives me 49, so that's nice because it's a complete square. Okay, so what we can do is we can replace these parts with a complete square, but before we do that, let's do the other part. And the second part is to set the numerator equal to some constant times the derivative of the denominator. So the derivative of the denominator is 2x plus 6, and then we add some constant b. So you do the same thing over here. So we're going to take 5x plus 3 is equal to some constant times, which you're going to figure out, plus b. And then what you do is you'll take the x terms, the coefficients of the x terms, the terms that involve x, and you'll set those equal to each other, and you'll do that with the constant terms. So for example, you'll have 4 is equal to something, and negative 5 is equal to something here. And then you can do the same thing over there. So I'm going to let you do those parts and figure out what a and b are. So remember, this is the derivative of the denominator. The same with that other thing. Because in this case, u is going to be equal to x plus 3. In this case, u is going to be equal to 45 minus 4x minus x squared. Well, yeah. Over here, I'm not going to have the arc tangent or the arc. I mean, I'm going to have the arc sine, but the other thing I'm going to be doing is, yeah, I'm getting confused here. Oh, yeah, the u for the part that involves the variable, you're going to end up with 1 over u du, and here you're going to end up with 1 over the square root of u du. Ultimately, that's what we're aiming for. Anybody? You guys confused, or you got an answer for me?
I'm
Confused? Okay. Okay. Well, let me do the one on the left-hand side, and then hopefully you can do the one on the right-hand side. Okay. Does everybody understand why I put that there, or how I got that? You take the derivative of the term in the denominator, not the. You don't have to take this form. You'll still get the same answer if you do it, but it's easier to take the derivative of the original expression because it's just a polynomial. Here it's a factored polynomial. So, I'm just taking the derivative of x squared plus 6x plus 23, which is 2x plus 6. Okay, so then what you do is it's really kind of an intermediate step here. Let me just move these down a little bit. So if you multiply out the right-hand side, you'll have 2ax. This 2x times a is 2ax. And then 6 times a, so you have 6a plus b. So now we have 3 terms. And these are the ones that use the variable x. Right? And then these are the constant terms. So you take the coefficients of the x part, which is 4, and 2a. And then you take the coefficients, which is negative 5, is equal to 6a plus b. And you can see that this one, I only have one unknown, so I can solve for a. So a equals 2. And then I can use a, plug that in down here. So I'll have negative 5 is equal to 6 times 2 plus b, or b is equal to negative 17. 12 minus negative 5 minus 12 is negative 17. So those are the coefficients. A is 2 and b is 17. So do the same thing here. Take the derivative of this, put that in there. You're going to have a negative sign in front of the x part. Then take the coefficients. So you'll probably want to multiply it out. So move it down. So go ahead and multiply these out once you've done them, and then group the coefficients appropriately. We'll use this. Do you remember doing partial fractions in pre-calculus at all, where you took a rational number with 2 factors in the denominator and you made it into 2 separate fractions? You probably did. To figure out what those coefficients are, you do some. It's kind of the same procedure that we're doing here. When the book does one of these problems, which I think they do one of them, they don't tell you how to do this. They just kind of say, oh, obviously, or something along, not usually obviously, but it follows. A lot of times it doesn't follow. You're like, what? It doesn't follow. I don't understand. So yeah, I'm listening to my BBC radio station. They're talking about Christmas, and so it reminded me of certain things. It's not really a pleasant memory, but you have certain foods that you have for Christmas. What, turkey, stuffing, mashed potatoes. Kind of like Thanksgiving and repeat, right? Does anybody have something other than turkey for Christmas? You have what? Ham? Anybody have roast beef? Sometimes. Lamb? Okay. So what I remember is either having roast beef or ham. No turkey. Which fine. I love lamb and roast beef. Like a standing, really good. That was good. And we would have boiled potatoes, not mashed potatoes, just boiled potatoes, and roast potatoes. Has anybody ever had roast potatoes? So the way my mother did it is you take like a 9 by 13 pan and you put vegetable oil in the bottom. Now, if you really want to be decadent, you put duck fat. Okay. I've never had it with duck fat. So you boil a potato. I guess you boil them. I think you boil them before you put them in there. I don't think you just put them in there unboiled. But anyway, doesn't really matter. And then so you put about this much fat in the bottom. So it comes up to whatever the oven temperature is, 350. And then you let it cook, and then every once in a while you take a spoon and you baste the potatoes, and they come out with it's like a big French fry, but even better. So that's one thing that we used to have. I like those too. The one thing I didn't like was Brussels sprouts. And that's apparently an English thing. I thought it was just things my parents did to torture me, because I hate Brussels sprouts. But they made me eat. Did you ever have to eat stuff did you have to eat stuff that you really didn't like? Yeah. So I don't know what you did, but I would hold my nose and I would eat it. And I would try to eat it as fast as I could, and then I would drink something, and then I would let go, And just because Brussels sprouts are really strong taste to them. Now my daughters like Brussels sprouts, and they're like, "Oh, it's just because you're cooking it wrong. You just need to roast them. They're much better roasted." And I've tried them roasted, and they're maybe about that much better. They still don't taste great to me. So that was the carrots. Yeah, I'm not a carrot. I just did one of the roast beef and the potatoes. That was it. Yeah. Anybody else got any? You said ham. Does anybody have any food interesting things? No, no, no.
That was just a positive head motion.
Yeah, yeah. The other thing too that the thing I didn't like, my mother made this. It's called a steam pudding, and I don't know exactly how you make it, but as the name implies, it's cooked by using steam, and it's usually a lot of times you can put in a jam inside of it, so it's like a steamed. I can't even think of an American thing that's like. Oh, the other thing I forgot was Yorkshire puddings. Does anybody have a Yorkshire puddings? Does anybody know what a Yorkshire pudding is? Okay, so I'm going to show you. So this, as the name implies, it's from Yorkshire, which is in England. It's pretty. It's easy. Well, it's not here. So we get a is equal to negative 5/2, and then you plug that into here, so we get 3 is equal to 4 times negative 5/2 plus b, and so that's going to be 3 is equal to negative, that's 5/2, 20/2, which is 10. So we get b is equal to 13. Okay, so that's now we got everything written. So what we can do now is we can put all that together, and let's do this one first. So you're going to take the original integral. You're going to take the coefficient for a, and we're going to put that outside of the integral sign. So the a coefficient goes here, and then you have the integral of 2x plus 6. So we're going to take a outside, and then you have 2x plus 6 divided by x squared plus 6x plus 23. So this one, the part that involves the variable x, we don't have to use the factored form. And then you have the second part, which is b. So you'll have negative 17 times the integral of 1, because I factored out the coefficient, divided by this version. So it's the factored version. So the original integral here becomes that. And if you multiply all this stuff out, you should get back to where you are. And you'll see we do. 2 times 2 is 4, so we get 4x. And then we get 2 times 6, which is 12, minus 17, which is negative 5. And the only difference between this denominator and this denominator is this one has completing the square, and this one's just the original version. So for this part, the substitutions we're going to use here is u is going to be equal to the entire denominator, and du is going to be equal to 2x plus 6 dx. And for the second case, u squared equals x plus 3 squared, so u is equal to x plus 3. A squared equals 14, so a is equal to the square root of 14, and du is equal to dx. So with those substitutions, the first integral is going to be 2 times the integral of 1 over u du, because this 2x plus 6 dx is du, and this whole thing is u. And the second part is going to become negative 17 times the integral of 1 over a squared plus u squared du, using those substitutions. So then what you do once you've integrated this stuff, the first one you'll get 2 times the natural log of the absolute value of u, and for the second part you'll get negative 17 times 1 over a times the arctangent of u over a, and then we'll have plus c for both of them. and then you can go plug back in. So plug u back in. So we go all the way up here for the green u. So we get 2 times the natural log of the absolute value of x squared plus 6x plus 23. And then we get 17 divided by the square root of 14 times the arc tangent of x. Oh, I'm using green. I should be using red. Okay, so you get 17 divided by the square root of 14 times the arc tangent of x plus 3 divided by the square root of 14 plus c. And that's the answer. So again, you're going to break it up into 2 parts. One where you're going to complete the square for the denominator, one where you're not going to use the complete square, you're just going to use the original polynomial. You use this type of equation to figure out what the 2 parts are, what the coefficients are. And those are going to be the numbers that go in front of the integral signs, a and b. So we set the numerator in the original expression equal to a times the derivative of the denominator plus b, set the coefficients of the x terms equal to each other. That's where you solve for a. Then once you have a, you can plug into the second equation, which is down here. You can't see it. And then you can then rewrite your original integral as 2 integrals and use the appropriate u substitution for each one. And just do what you normally do. Okay, so the rest of it's just stuff we know how to do. Okay, so the next one, so we're going to look at this one. We have this one's a definite integral, so this is a little more difficult. But what I want you to do is I want you to rewrite the original integral as 2 parts. One that involves the square root of this, and one that involves the square root of 49 minus x minus 2 squared. So just first thing you do is, before we get any further, is to rewrite this integral here as 2 integrals. And we won't change the limits yet. So it's going to be, and the second one is negative. No, actually the first one's negative because you've got a negative a. So, and b is positive. So the second one is going to be positive something. And one part involves the square root of 45 minus 4x minus x squared, and the other one involves the other one, which is 49 minus x minus 2 squared dx. Actually, we're going to have to move on this because we're going to run out of time. I might have to. We'll set it up, then I'll hand the test back, and if we have time to finish it, we will. So, okay. So a is negative 5 halves, and b was 13. And this is going to be here. Here the numerator is 1, and here the numerator is going to be. Did I do something wrong here? Did I copy something wrong? Yeah, this should be plus. Okay. So that should be plus. I don't know why I did it the other way. Okay, so here the numerator is going to be negative 2x plus 4, and the numerator over here is 1. So they have to have the derivative of this being the numerator. And here the the numerator is just 1. So the substitutions you're going to make here is u is equal to 45 minus plus 4x minus x squared. So du is equal to negative 2x plus 4 dx. And here u squared is equal to x minus 2 squared u is equal to x minus 2. A squared equals 49. A is equal to 7. Du is equal to dx. So when you make these now you're also going to have to change the limits, and you're going to have the limits are going to be different because I'm going to have different substitutions. So when x equals -1, u equals something, and when x equals 6, u equals something, and the same down here. So when x equals -1, u equals, in this case, -3, and when x equals 6, u equals 4. So I'm just taking this. So -1 minus 2 is -3, and 6 minus 2 is 4. Over here, I'm going to have to plug it into this equation. So it's going to be 45 minus 4 minus 1. So that's 40. And if I plug 6 in there, that's going to be 45 plus 24, which is 69. 69 minus 16, or 36. 69 minus 36 is 33. Is that right? Somebody want to double check me on that one? I'm doing that in my head. 45 minus 4 minus 1. Yep, okay, that's right. 45 plus 24 is 69. 69 minus 4 is, wait a second, that might be wrong. That's wrong. The second one's wrong, right? So if I plug in 6, I'll have 45 plus 24, which is 69. 69 minus 36. 69 minus, no, it is right. It is 33. Okay, so ultimately what you're going to have -5/2 times the integral from 40 to 33 of 1 over the square root of u du. And then you're going to have the second integral is going to be plus 13 times the integral from -3 to 4 of 1 over the square root of a squared minus u squared du. So you got to use the appropriate limits for the appropriate substitution. And then, so what you'll get here is you'll get 5/2. The integral of this, you got u to the -1/2 power. So that's going to be u to the +1/2 power divided by 1/2, evaluated between 40 and 33. I wrote that down wrong. 33 plus 13 times the arc sine of u divided by 7, because a is 7, u over a, and that is evaluated between -3 and 4. And then you would just plug the numbers in. Okay, so I'm going to, if you want to try to finish that while I am handing out your tests. So each problem is worth 20 points. And so there's 220 total points. So I compared the numbers of the last year's class. You guys actually did a little better than last year's class. So that was good. Okay. Anyway, I don't know what the answer to this is, but all you need to do is plug the numbers in, which you can do. Before we go over the test, I'm going to the one type of problem that's on the exam which has not been on a previous test is if you're given some function like x squared to figure out the derivative using the limit definition. So go ahead and make sure you review that. So that's from chapter 2. So it's the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. I'm not going to work through it. Just go back and study that. Okay, so as far as the test is concerned, most people